Okay. So now is the most important postulate in quantum mechanics. I remember vividly, when I took the analog of this class, it was called Physics 143A at Harvard, and the professor at this point said, I know him well now, he's a friend, he said, "This is what quantum mechanics is all about." And I was so psyched, and then he told me, and it was like, that's ridiculous, seriously? That's what quantum mechanics is all about? So I always thought like this is some weird thing where like old physicists go crazy, but it turns out, I'm gonna say exactly the same thing. This is the most important thing in all of quantum mechanics. It is all contained in the following proposition. Everything. The two-slit experiments, the box experiments, all the cool stuff in quantum mechanics, all the strange and counterintuitive stuff comes directly from the next postulate. So here it is. I love this. 3. Put a star on it. Given 2 possible wave functions or states, I'll say configurations of a quantum system. We're sort of like right in the Valkyries, you know, playing in the background. So, of a quantum system corresponding to 2 distinct wave functions. F with an upper NS is going to be my notation for functions, because I have to write it a lot. Psi1 and Psi2. I'll say of X. The system can also be in a superposition of Psi1 and Psi2. Where alpha and beta are complex numbers. Given any 2 possible configurations of the system, there is also an allowed configuration of the system corresponding to being in an arbitrary superposition of them. If an electron can be hard and it can be soft, it can also be in an arbitrary superposition of being hard and soft. And what I mean by that is that hard corresponds to some particular wave function. Soft will correspond to some particular wave function. And a superposition corresponds to a different wave function, which is a linear combination of them. Yeah? Yeah, okay, that's a very good question. So A and B, alpha and beta are some complex numbers subject to the normalization condition. So indeed, this wave function should be properly normalized in the end. Now, let me step back for a second. There's an alternate way to phrase the probability distribution here, which goes like this, and I'm going to put it here. The alternate statement of the probability distribution is that the probability density at x is equal to psi of x norm squared divided by the integral over all x dx of psi squared. So notice that if we've properly normalized the wave function, this denominator is equal to 1. But if we haven't properly normalized it, so it's not there, right? And then it's equivalent. But if we haven't properly normalized it, then this probability distribution is automatically properly normalized, because this is a constant. When we integrate the top, that's equal to the bottom. It integrates to 1. Cool?